Hi everyone, my name is Černý. Thank you all for coming, and I would also like to thank my collaborators, Dan Macha from the Institute of Paleobiology in Warsaw, Poland, and my PhD advisor, Graham Slater at the University of Chicago. So today I'm going to be talking about the Ornithischia dinosaurs, which you can see in these pictures here. They are also called the bird dinosaurs in reference to their pelvic morphology, but they are actually only distantly related to birds. And until recently, they were universally agreed to be one of the two major dinosaur subclades. So here we can see some of their representatives. At the top, there are the ceratopsians, or the horned dinosaurs. We have an ankylosaur on the bottom left, and on the bottom right, there is Ornithischia, which is believed to be related to both the horned dinosaurs and the duckbill dinosaurs, also called the ornithopods. Actually, this started out as a very different talk originally. The original motivation for focusing on the Ornithischia dinosaurs was this study published by Sakamoto et al. In PNAS 3 years ago. And in that study, they found some quite complex multi-level macroevolutionary dynamics for this clade. Specifically, using phylogenetic-based generalized linear mixed models, they suggested that Ornithischians as a whole entered a period of decline, just like other dinosaurs, already in the early Cretaceous, long before their final extinction at the KBG boundary. But they also suggested that two of their subclades actually continued to diversify quite rapidly all the way until their final extinction. And they speculated about how this might have been related to their food processing morphologies. So for example, the quite complex and mammal-like dentition of the group called the hadrosauriforms. And the original motivation behind this talk was really just to retest these hypotheses about Ornithischia diversification using state-of-the-art approaches that have become available in the meantime, specifically pyrate and fossil BAM. These approaches have several advantages compared to traditional paleontological methods, which usually rely on counting species within time rings. Specifically, they explicitly treat fossils as the results of the same generating process that also gave rise to extant taxa, making it possible to combine both sources of information in a single analysis, provided that they are available. They are also both implemented in a Bayesian framework, which makes it easy for them to accommodate multiple sources of uncertainty. And we are especially interested in seeing how the results of these two methods would compare to each other, because while BAM relies on time-calibrated phylogenies, pyrate does not. So we were interested in seeing whether incorporating phylogenetic information would make a difference. So first, we actually needed to infer a time-calibrated Ornithischian tree. For that purpose, we used two of the largest morphological matrices available, those of Han et al. 2017 and Maja et al. 2018, both of which contained about 60 to 70 tips and several hundred discrete characters. And after reanalyzing these matrices, we found out that the results were topologically suspect. Specifically, Rexamel, Parsimony, and Mr. Bayes, or the time-free analyses, seem to agree with each other and with the traditional phylogeny, but the sampled ancestor beast-to time tree did not, as you can see here. So both the intersecting lines and the dashed branches represent topological conflict. But in the absence of anything better to go off, we decided to conduct our downstream analyses using time trees that were either topologically unconstrained or fixed to the topology of the Rexamel analysis. All right, so for BAM, we found a single rate regime governing the entire 120 plus million year long history of the clade. The only thing we got is this exponential decay from the red, meaning fast, rates at the root, toward the blue, meaning slow, rates at the tips. But it just reflects the way BAM models time varying rates. With pyrate, the results were less clear and highly dependent on the model averaging algorithm that we used. And before I show you the results, just a quick note on visualization. So for model probabilities across replicates, I'm going to represent them using the stacked bar plot, and the probability of a given number of distinct traits is going to be proportional to the length of the bar segment of a given color. The rates through time plots should be pretty self-explanatory. Okay, so with the bird-dead MCMC algorithm, the evolutionary history of the Ornithischians also seems to be pretty uneventful. What we get are mostly flat speciation and extinction rates through time, and no great shifts aside from some edge effects. However, for the reversible jump MCMC algorithm, which the authors of Pyrate consider to be more reliable, we actually had some trouble reaching stationarity. But when we did, we recovered a large number of distinct traits and a set of spurious rate shifts which seem to have no clear biological interpretation. And one idea we had at this point is that perhaps what's happening here is Pyrate mistaking changes in the rate of speciation for changes in the rate of fossil preservation or fossil sampling. That could explain, for example, this interesting increase that you can see in the rate of speciation in the Middle Jurassic, which was a period of very low preservation for pretty much all terrestrial vertebrates. So we decided to test this idea using some simulations. Specifically, we simulated two simple scenarios of 7 replicates each. So in our first scenario, we held the rates of extinction and sampling constant, but allowed for a twofold increase in the rate of speciation 70 million years before the clade went extinct. And here you can see an example of a phylogenese simulated under this scenario, and not just the phylogeny, but also its corresponding fossil record. So each of those little black rectangles represents one fossil occurrence. In our second scenario, we held the rates of speciation and extinction constant, but allowed for a 5-fold decrease in the rate of fossil sampling at the same time horizon. And we used rejection sampling to ensure that our simulations would be as close as possible to our empirical Ornithischia data in terms of the total number of fossil occurrences, the proportion of species surviving all the way to the end, and clade age. Our simulations were actually more optimistic than our empirical data in terms of the total number of species and in terms of the percentage of singletons. So if it was one of those two variables that were responsible for the strange results we got, the analyses of simulated data should produce more reasonable results. And before I show those results, just one more note on visualization. The model comparisons are going to look pretty much the same, except that this time I'm going to mark the true number of rates in black. So basically, the more black you see, the better, because black represents the probability assigned to the true model in these analyses. So for the first scenario, where there were two distinct speciation rates, we see that it does pose some problems to Pyrate. One of those would be the overestimation of the number of distinct extinction rates. So we see that Pyrate never really is able to recover the fact that there was just one. For 3 out of 7 replicates, we are able to correctly identify that shift, that increase in the speciation rate. But for the remaining 4 replicates, it's just completely flat through time. On the plus side, there seem to be no spurious rate shifts, and that's also true of the extinction rate. When we go over to the second scenario, where there was only a single speciation rate, but 2 distinct rates of preservation, we see that Pyrate doesn't really perform well. So again, in 3 replicates out of 7, we are able to correctly recover the flat rate of speciation, but in 4 replicates, it seems that what's happening is Pyrate mistaking the drop in the rate of sampling for an increase in the rate of speciation. Specifically, what's happening is that this decrease in the rate of sampling led Pyrate to infer shorter average species longevities and then overcompensate for that by increasing the postulated speciation rate. However, that cannot be the whole story either, because in 3 replicates out of 7, we also see these spurious rate shifts which have no support in the data whatsoever. And if we look at extinction instead of speciation, the situation looks very much the same. Okay, so that was Pyrate. What about BAM? Well, for that first scenario where there was a rate shift, BAM was never able to find it. And the posterior support for the 0 shift configuration was actually even increased compared to its prior support. And setting the mean prior number of shifts to the number of branches crossing that minus 70 MA time horizon did not help either. On the other hand, in about half of the cases, 13 out of 28 replicates, BAM is at least able to identify the correct tendency, meaning an increase in the speciation rate going from the roots toward the tips. It's just that instead of recovering this increase as a distinct specific rate shift, it smears it across the whole evolutionary history of the clade. This is not the case for the second scenario, where there was only a single speciation rate, but a drop in rate of preservation, where the trend is always decay of this net diversification rate from the root toward the tips. And one thing that also should be mentioned is that there is no clear relationship between the number of tips and inferential success. So there are small trees which get it right, and large trees that get it wrong. And if you're interested in the specific proportion, 4 out of 14 small trees were able to recover the correct tendency, 9 out of 14 intermediate trees were able to recover it, and 4 out of 7 large trees were able to recover it. So perhaps there is some trend, but it's not really all that clear. So to sum up, both BAM and pyrite seem to be problematic when applied to a simulated scenario that corresponds to our knowledge of a well-studied fossil clade. Both of these methods seem to do slightly better when it comes to inferring general tendencies rather than the exact number and location of clade shifts, but even there, their performance is unsatisfactory and insufficiently understood. For pyrite, the problems perhaps have to do with parameter unidentifiability, specifically the inability to distinguish between the rate of speciation and rate of sampling. For BAM, the simplest explanation is that a small number of tips won't give you solid results, but that doesn't seem to be the whole story here. In conclusion, we still have no idea of what's going on with the Ornithischia. The results of the two methods are totally incompatible, and based on the simulations we ran, completely untrustworthy. So, based on that, we would like to urge caution when applying these methods to entirely extinct clades, and analyses that have already done so may need to be viewed with skepticism. And with that, I would like to open the floor to questions.
What kind of results would you predict if you used time constant BAM rather than the sort of exponential camera?
If I use time constant BAM, I would hope to see, again, a single shift, or a number of shifts corresponding to the number of branches crossing that time horizon for the first scenario, where there actually were two distinct speciation rates, and no shift in the second scenario.